Glad to see you again for this third lecture of the course on process mining, data science in action. Today we will see how process mining relates to data mining. Process mining, as I explained in the last lecture, is the missing link between model-based analysis, process model-based analysis, and data-oriented analysis like data mining, with the goal to answer performance-oriented questions and compliance-oriented questions. So one can think of process mining as superglue. It's the glue between data and processes. It's the glue between business people and IT people. It's the glue between business intelligence and business process management. It's the glue between performance and compliance. And you can do this at runtime and at design time. So it's connecting many different things, and that makes it so incredibly valuable. This diagram gives a kind of overview showing that process mining is this world, this discipline, connecting business process management to classical data analytics like data mining. And as we have seen in the last lecture, process mining consists of different types of mining, and here you can see process discovery and conformance checking. Later we will also look at predictive analytics, how you can use process mining to predict things about the future. If you see this diagram, you may ask yourself the question, how about BI, business intelligence? Well, if you look at the classical BI tools, they tend to show only spreadsheets, meters, graphs. They try to capture reality in a set of numbers, and that is not sufficient. This is illustrated by Anscombe's quartet. That's the four diagrams that you see here, and let me explain what we are seeing. We are seeing four different data sets, each consisting of 11 elements. They look very different, but if you look at their statistical properties, they are almost the same. So if we look at the mean x-coordinate of these 11 elements, in each of the four cases, the mean is 9. The variance is 11. If we look at the y-coordinate, we also can see that all of these four diagrams are exactly the same. Even when we apply linear regression, all of these four data sets yield exactly the same result. So this is illustrating if a BI tool is just showing numbers, that is often not sufficient. You have to look behind the numbers because things can be very different. One can think of process mining as finding desire lines. Here you can see a photo that I took at the campus of Tsinghua University in Beijing. And here you see one of my colleagues there walking over a desire line. So this is a trail in a grassy area that is showing what people really do. So the trail can be seen as the event data, and the sign saying that you should not walk there, that you should use the official route, can be seen as the process model. So this is an illustration of what process mining tries to do. You try to uncover the desire lines. What do people really do? And you can find very surprising things. So for example, if you look at this desire line, it is clearly showing that people do not follow the process model. The gate that you see here is aimed of keeping cyclists out of this park. But what you can see is that the desire line is showing that people do not follow the things that they should do here. So the gate does not work as it is supposed to work. So using process mining and conformance checking, you can use and show these types of things. Now it's time for a demo that we can see process discovery in action. Let's take a look at an example of process mining in action. What I see here is that I load an event log into the process mining tool PROM, and I apply one of the standard process mining algorithms in PROM. I'm applying the so-called fuzzy miner, and based on raw event data, I automatically learn a process model, as you can see here, and it goes incredibly fast. We can zoom into the model, we can look at the different activities, and the arcs connecting the activities are showing how cases are flowing through this process model. We can zoom in and zoom out, just like when you use Google Maps. So now I look at the same process model at a higher level of abstraction. We see fewer activities because we only show the frequent activities at the highest level. We can also replay reality on such a model. So I'm now loading both the model that I discovered and the event log, and I'm applying a so-called replay algorithm on it. So what you now see is not a simulation. What you're seeing is that we are replaying reality on top of this model. So all the white dots refer to real cases. What we can see, you can see the numbers next to the cases, we can follow individual cases, we can see all the events, we can see congestion in the process, we can see frequent paths and infrequent paths, and I think this is a very nice illustration that without any modeling, you can see what is happening in reality through process mining. So let's take a look at another metaphor showing what process discovery is all about. You can compare process discovery to learning a language based on examples. So here you see a mother, and the mother is saying sentences to the child. So the mother is saying A, B, C, and the child is trying to learn the language. So if the mother would always say just the words A, B, and C, the child would think, okay, this language is A, B, C, and that's all that exists. Then if the mother would say an A, B, D, the child will think, oh, at the end there is apparently a choice between C and D. So this child is very smart, thinking already in terms of regular expressions. So this is the model of the language that the child infers. Then the mother says another sentence, AD. So now the child has to think, what could this language be about? So it's apparently A and D, or it is A, B, and then followed by C or D. Now the mother says A, B, B, C. Another example, trace that we can observe. And now the child makes a jump in learning and infers that apparently the number of B's is variable. It can be 0 or more, etc. And so the mother says more words, and if it fits into the language, then the child has a good understanding of that language. So in this example, we can see a sentence and compare that to a trace in an event log, and we can think of the language as the process model. So this is the relationship between understanding a language based on examples from learning a process model just by looking at examples. What we saw in the last lecture is that next to process discovery, we also have conformance checking. In that case, you want to see how does reality deviate from the modeled process. You can compare that to spell checking. So the spell checker has a model of the language, and you type a piece of text, and then it is checked whether that piece of text fits the language, as it has been formalized. This can be compared to the typical diagnostics that you get when you do conformance checking in the area of process mining. So you see the activities that have happened but that should not happen, or the other way around. Or you will see activities that were executed too late or too early or by the wrong person. This can all be compared by spell checking. So in the remainder of this week, we will focus on the topic of data mining. As I have explained, also in the previous lecture, process mining is very different from the classical data mining techniques, but there are many relationships. So in this course, you will also get a basic understanding of what process mining is all about. And of course, also data mining. So the growth of the digital universe is driving the fact that many people are using data mining techniques. initially the term data mining had a very negative connotation. People talked about it as data snooping, phishing, etc. As statisticians did not consider it the proper way to do. But this is now a very mature discipline driven by these huge amounts of data. But data mining is data-centric and not process-centric. So let us take a look at some typical data sets and then try to think what data mining can do. So what you see here is a data set of more than 800 persons that have died at a particular age while having a particular weight, and it was recorded whether they were drinking or smoking. So for example, the first row corresponds to a person that died at the age of 44 while being a drinker and a smoker and having a weight of 120 kilos. So this is an example of a data set, and the types of questions that you can ask about such a data set are things like, do people that smoke also drink? When do people get old? What kind of properties do they have in common, the people typically that get older? So what is the impact of a certain lifestyle on the life expectancy of a person? So this is one data set and typical data mining questions. This is another data set, and every row now corresponds to a student at the university. And what we see here are different columns referring to different courses. We can see the marks that people got for each of these courses. We can see the duration of their studies in months, and we can see whether they passed, failed, or graduated cum laude. So again, if we have such a data set, we can ask all kinds of questions. So are there certain courses that are typically taken together, or do marks of different courses highly correlate? If people fail, what are the typical courses that are leading to such a failure? When and why do people drop out? It's a different type of analysis that you can do based on such a data set. But we can look at all kinds of other data sets. So here you can see the different orders in a cafe. So every row refers to an order. So if you look at the first row, you see a person that has ordered a cappuccino and a muffin. So every row corresponds to an order. And again, you can try to learn all kinds of things. So you can try to find out which are the products which are typically purchased together. You could try to find out, are there characteristic groups of customers that typically consume similar things? And all of this can be used to try to promote sales. So these three data sets give all kinds of examples for data mining problems. So if we look at the raw data that we get in each of these examples, is we get a table. Every row in the table corresponds to an instance, and every column in the table refers to a variable, often called attribute or feature or data element. If we look at these variables, these columns, then we can find two main groups: numerical variables that refer to a number, like for example an age or a weight, and categorical variables that don't have a value that is a number, but these are values taken from a smaller set. So for example, cum laude, passed or failed, or true and false are examples of categorical variables. If they have an order, they are called ordinal. If not, they are called nominal. So these are the variables, the columns that we see in a data mining problem. So to check whether you understood what I just explained, take a look at this data set. And my question is, what columns refer to ordinal categorical variables, which to nominal categorical variables, and which ones are numerical variables? So please think about this for a minute. So the answer to the question is that there are two categorical variables referring to the first two columns, whether people are a drinker or a smoker. These are not numbers, and they are nominal because true and false do not have some natural order. There are two numerical variables, the weight and the age, because they refer to a number. There are two types of data mining techniques, generally referred to as supervised learning and unsupervised learning. In the context of supervised learning, we have labeled data. And labeled data means that there is a response variable that labels the instance. And the goal of supervised learning is to learn from the other variables that are called predictor variables what the response variable is going to be. So instead of response variable, we also talk about dependent variables, and instead of predictor variables, we also talk about independent variables. And the goal is to explain the dependent variable in terms of the independent variables. So classification techniques like learning decision trees aim to answer such questions. So what is the class depending on the set of variables that we know? If the response variable is numerical, we typically use regression techniques. And then the goal is to find a function that explains the response variable in terms of these other variables. So let's take a look at this data set. So from every instance, it refers to a person, and we know whether the person was drinking or not, smoking or not, and we know the weight. We would like to learn the influence of drinking and smoking on somebody's body weight. If you have that question and you think of supervised learning, what are the response and predictor variables? I think the answer to this question is relatively easy. In this particular example, the response variable is the weight, and we would like to explain the response variable in the predictor variables, whether people are drinking or smoking. Next to supervised learning, we also have unsupervised learning, and now the data is unlabeled. In other words, we don't have response variables. And the typical techniques that you will then look at are clustering and pattern discovery. So you want to find homogeneous groups of, for example, patients or customers, without aiming to look at a particular response variable. And these are just some examples of the many data mining questions that you can ask. And in the next lectures, we will zoom into some of these questions, and I will teach you hands-on knowledge to solve these types of problems. There are many data mining tools available. You can see some of them here. In my next lectures, I will use RapidMiner to illustrate these classical data mining techniques. You don't have to install RapidMiner for this course, but if you want, you can do, and you can repeat the experiments that I will show. There are many differences between process mining and data mining. And let me repeat some of the things. In what way are they common, and in what way are they different? They both start from data. But data mining techniques are not process-centric. They look at isolated decisions of the type that I've just shown to you. Topics such as process discovery, conformance checking, bottleneck analysis, and all the other things that I showed in the previous lecture cannot be done using traditional data mining techniques. So you need to have process mining for that. End-to-end process models are crucial, and when you want to discover end-to-end process models, concurrency is important. So when we will talk about process models, we will deal with the topic of concurrency, because it's very important. Process mining assumes a different type of data than the data that we have just seen. We assume that we can see events. These events, they have timestamps and they refer to cases. And that is a crucial difference with the three data sets that I showed to you before. But process mining and data mining can be combined to answer very advanced questions. So that's very important. If you would like to learn more about data mining, and in the next lectures we will discuss some of the techniques in more detail, please read chapter 3 of the process mining book. Thank you for watching and hope to see you soon.